students, welcome to AMIT'S Center. Today we are back with our chemistry chapter, that is topic D block elements. In the periodic table, elements are divided on the basis of their properties, S, P, D, and F blocks. Okay, in the periodic table, S, P, D, F block, and D block is present in between S and P block. S block and P block in between D block is present. Okay, and these D block mainly include metals. With some exception cases, these mainly include metals, and we have to discuss in this video D block, all about the D block element, what are their properties and how they behave, how they react, which are the physical properties, what are the chemical properties, with some exceptions, some length height contraction. And so first of all, question is why they are called transition elements. D block elements are said to be transition elements. In the D block this D block include empty, some partially filled d orbital. These elements include partially filled d orbital is included in the D block elements. So, due to the presence of the partial field, means some unpaired electrons are present in the D block. In the S block, 2 electrons should be occupied. In the P block, 3 electrons, 1, 2, 3, 4, 5 and 6. 6 electrons should be occupied. But in the D block, 1, 2, 3, 4, 5, 5 substrates are present, and in total 10 electrons should be occupied. And in the D block elements of the D block include incomplete d orbital, means some 7 electrons are present, 8 electrons are present. Due to the presence of the unpaired electrons, electrons are shifted from the lower level to higher level due to their greater instability. That is why transition means. Transition is the jumping of the electrons, and due to the presence of the unpaired electrons, some partially filled orbital, d orbital, electrons are shifted from the lower energy level to the higher energy level. So that is why they are called the transition elements. They are called transition elements. Okay. So in the D block is divided on the basis of the first transition series, second transition series, third transition. In the first transition series, 3d orbitals are gradually filled and 4s orbitals is already filled up. In the second transition series, 4d substrates are gradually filled, 1, 2, 3, 4, and 4s again 5s is already filled up. And in the third transition series, 5d substrate is gradually filled, 6s is already filled up. Okay. So the general electronic configuration of the D block elements की general electronic configuration is N-1, D 1 to 10 and Ns 1 to 2. In the D orbital, electrons are gradually filled up, and S orbital includes 2 electrons. Okay. So in this elements of the first of all, we will write the elements of the first transition series, that is cadmium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper and zinc. And this one atomic number is 21, 22, 23, 24 and so on, 25, 26, 27, 28, 29, 30. So This d orbital occupies one electron from the s orbital and and the configuration will become 3d5 instead of 3d4, and again 3d manganese 3d5 4s2, 3d6 4s2, 3d7 4s2 cobalt, 3d8 4s2 again instead of 3d9. D subshell will occupy one electron from the s orbital and it will become 3d10, and this is 3d10 4s2. And the question here comes out, why chromium and copper shows this chromium and copper shows anomalous behavior. Means anomalous means something different, as all the electrons occupy the one electron. The one electron is gradually filled up in the d subshell, moving from scandium to zinc. But some exceptional cases are seen in the first transition series. The question is why? Because answer here is empty, half-filled or fully filled subshells are known to be most stable. Empty, half-filled and fully filled. Fully filled. Our subshells are said to be most stable. These are the most stable. So the element wants to be stable. Therefore, it occupies one electron from its corresponding subshell and leads to its more stability. So that's why they both show anomalous behavior. Now we will discuss some general properties of the d block elements. So first property is atomic radii. Along the period, as the atomic number decreases with increase in the atomic number. Atomic radii decreases with increase in the as atomic number increases. For example, let us take example of scandium, titanium and vanadium. 3d1 4s2, 3d2 4s2, 3d3 4s2. So as by this atomic number is 21, 22 and 23. By increase in the atomic number, the attraction. So suppose this is the nucleus, and these are the orbitals, and the attraction. This is the electrostatic attraction. What is electrostatic attraction? Increases with increase in the atomic number because electrons are added in the d subshell. Electrons are being added in the d subshell. So by adding these electrons, this is the 4s is the outermost orbital. This is the outermost shell. So electrons are shielded from the inner nucleus. The outer. This is the 3d orbital, and so this is the 4s orbital. Due to the electrons present on this 3d orbital, this attraction between the nucleus and 3d orbital subshell increases. Electrons are attracted towards the nucleus as electrons are added in the 3d subshell. So this will screen the 4s electrons. 3d electrons will screen 4s electrons, but screening effect of d or subshell is not much stronger. Screening effect of 3d subshell is not much stronger. So 4s orbital also feels some attraction towards the nucleus. So electrons get attracted towards the nucleus, size decreases, so the atomic radii decreases with the increase in the atomic number. So but outermost forest subshell decreases, so the attraction decreases. With decrease in attraction, electrostatic attraction, size increases. Therefore, as the size increases, atomic radii decreases. So here the question arises is, what is lengthened contraction? Now the question is, what is lengthened contraction? I have already written the definition of what is lengthened contraction. That is, atomic radii of second and third transition series are expected to be nearly same. Means as the atomic radii of second transition series is more than the first transition series, because as I have already written examples on the board of the first transition series, here 3D subshell is gradually filling and here 4D subshells are gradually filling after filling the 4s2 subshell. So with increase in the subshells, the electrostatic attraction between the nucleus and the outermost electrons decreases, and as the attraction decreases, atomic radii increases. Therefore, atomic radii of the second transition series are greater than the first transition series, and this is expected to be same for the second and the third transition series, as the atomic radii of the third transition series is expected to be greater than the atomic radii of the second transition series. But this does not happen. The atomic radii of both first, second and third transition series are expected to be nearly same. Why? Because as the subshells are gradually increasing, 4D and here 5D subshells are gradually filling, but due to the intervention of this 4f orbital in the third transition series, instead of 5D, first of all 4f subshells are gradually filling. This filling of the 4f subshells leads to the decrease in the attraction, increase in the attraction between the outermost electron and the nucleus. So I have written on the board, this is because the intervention of the 4f orbitals, which is filled before the 5d. Before filling 5d, we have to first of all fill 4f subshell. Filling of 4f orbital before 5d results in the decrease in the atomic radii. Therefore, the decrease with increase in the subshell at the same time leads to the decrease in the stability, decrease in the atomic radii. This is known as the lengthened contraction. Now our next property is metallic character and enthalpies of atomization. So metallic character, as I have already said, deep lock elements are all metals. So they are metals. They will show the properties of they are metallic in nature. They will show all the properties of metals. That is, they are ductile, they are sonorous in nature, they are malleable, they can be divided into sheets, and they are very shiny, and they are very hard. Their melting and boiling point is expected to be much harder, as the bonding is much stronger. And next question is enthalpies of atomization. First of all, what is enthalpies of atomization? It is the tendency or the heat required to remove an electron from that element. As electrons are gradually filled up in the element, that is 3D subshell is filled, 4D subshell is gradually filled up, 5D is filling up, and we have to remove any electron from the 4s or from the 3D orbital, from the 4s or the 3D or 5s and 4D, and from the first, second or the third transition series. It is the tendency, I am writing, this is the tendency or heat required to remove electron from its outermost orbital. So with increase in the atomic number, electrons are increasing. So as the electrons are, but as atomic radii, first of all decrease. decreases, and after midway it increases because electrons are getting far away from the nucleus. So the electrostatic attraction between the nucleus and the outermost electron decreases as there is less attraction. So electrons can be easily detached from the outermost electrons. So enthalpies of atomization after midway decreases. Before midway it increases, and after midway it decreases. So metallic character, they all are the metals and enthalpies of atomization. Next property is the melting point and the boiling point. Third property is melting point and boiling point. As already said that the d block elements are metal, they are metallic in nature, and in metals bonding is stronger. Electrons are much closer to each other. Electrons are bonded as unpaired electron. More is the unpaired electron. They get bonded to the another element which are also having unpaired electron to form covalent bond, strong covalent bond. More is the unpaired electron. More is unpaired electron. More is the melting point or boiling point. Greater is the unpaired electron, greater is the melting and the boiling point, because with increase in the unpaired electrons they form stronger covalent bond with the other elements, therefore their melting point and boiling point increases. Next property is the formation of the colored ions. It is seen that most of the transition d block elements form colored compounds. They form colored compounds, exception one or two compounds which are having filled d orbital does not show any color. They are white in color, except that both d block elements are colored in nature. Why they are colored in nature? Why they form colored ions? Because as the ion approaches the center, as the ionized ion approaches the central metal ion, the excitation of the d orbital, as d orbital in the same subshell does not have this equal energy, d orbital splits up. D orbital in same subshell does not have equal energy. D orbital splits up into its two orbitals. D orbital, as the d orbital contains 5, 1, 2, 3, 4, 5, and these are split up into the energy levels according to their energy levels. The orbitals are dxy, yz, dzx, and here dx square minus y square, and here dz square. Yeah, this is not